great pleasure to welcome all of you here to Ari Jules. Ari Jules is one of the leaders in cryptography, applied cryptography and computer security. He's currently chief scientist at RSA Labs. If you know anything about computers or computer security from an industry perspective, you've probably heard of RSA and RSA Labs. Ari is also very research touches a broad area of computer science and computer security, all the way down from embedded systems and RFIDs, in fact, publishing a paper this week on RFID security at another conference in San Diego, all the way up to security for cloud computing, which is what he'll be talking about today. In the spirit of computer science or computer security research, Ari also does a bunch of work on both understanding the vulnerabilities in existing systems and future systems so that we can understand how to build stronger and more secure systems in the future. And so Ari does work on both finding vulnerabilities and on defenses. And he's, again, very broad. And one of the things that he is interested in the future is the relationship between computer security and psychology and authentication and so on. I know I kind of used the term Renaissance person in computer science and computer security in the past, but I think Ari is a real example of that. Because not only does he do computer security research, he's a published fiction author of the book Tetractys, which if you read the reviews, some people refer it to as like the Da Vinci Code with actual scientific technical foundations for it. He has a degree in Latin literature, and he's also a past fencer and still welcomes all comers. So, if you don't like the talk, be careful. That was directed at them, not you, but I was pointing at you. And also, Ari was a member of the TR100. The TR100 predates the TR35, and he was one of the first classes of the TR100 young innovators. So has had a lot of recognized impact for his work, too. So with that, it's a great pleasure to welcome Ari to talk about security.
Thank you, Yoshi. Thank you. I'm very happy to be here today. I'm going to talk about two opposing forces in cloud computing. Aggregation, the drawing together of resources, and distribution, the dispersion of resources, and their impact on security. In particular, I'm going to talk about a couple of the vulnerabilities created by aggregation and the ways in which distribution can help dissipate some of these vulnerabilities. One of the beauties of the cloud is the nice, clean, crisp abstraction layer it presents to the user. As a tenant, you can spin up a virtual machine, for instance, and operate it with no knowledge of its architectural underpinnings or of the surrounding environment. This simplicity, though, of course, covers up a lot of complexity and a lot of messiness. And so when you spin up a VM, it's not, in fact, operating in isolation, even though it looks that way to the tenant. This VM is most likely sitting on a server, a physical host, with the VMs of other tenants. And of course, you know nothing about these other tenants. You don't know anything about the strange bedfellows you may end up with in the public cloud. Right? This situation, so this is an example of aggregation, of course, so drawing together VMs. This situation is replicated, of course, across an entire data center and across the cloud in general. There are other forms of aggregation as well that affect cloud computing and other forms of computing. For example, the password you use to access resources remotely in the cloud, for instance, is also not present in isolation in a database. It's sitting with the passwords of many other users. Collectively, all of these passwords, these thousands, hundreds of thousands of millions of passwords, are sitting in a single database, meaning a single point of compromise and a very attractive target for a potential attacker. Right? This essentially means one-stop shopping for an attacker who's looking to go after passwords. So these are the two forms of aggregation I'm going to talk about today. And I'm going to begin by talking about an attack enabled by the first form of aggregation, namely this drawing together of virtual machines. I'm going to talk about joint work with those listed here, and thanks to Inchin for providing slides. This was presented at ACM CCS late last year, this work. The problem, to remind you, is co-residency on a physical server. It's frequently the case that we have multiple VMs making use of the same hardware. They're managed by a hypervisor. And this hypervisor is responsible for providing security isolation. And this is how virtualization works. The hypervisor creates a boundary, a logical boundary between the two virtual machines, although they do share hardware. So the question naturally arises, if one of these VMs is malicious, wants to exploit the other VM. What can it do? What can it do by merit of the fact that the two share hardware? How strong is this isolation boundary? Well, for some time, there's been an interesting open problem here. Are side channels possible to exploit in this kind of virtualized environment? And of course, since I'm speaking to you today, the answer is yes. The most devastating possible side channel would be one in which the attacker exfiltrates from the victim a cryptographic key. And that, in particular, is what I'm going to talk about today. I'm going to talk about how we can extract a cryptographic key, a private El-Gamal key, from a victim in this type of environment. The attack is pretty complicated. I'm going to gloss over a lot of details. But roughly speaking, it proceeds in 4 stages. The first stage is known as priming and probing. And this technique is common to a large swath of side channel attacks, known as access-driven attacks. The idea is fairly simple. The attacker first primes the cache, sets up the cache, by running some code that fills all of the cache lines. So it colors the cache pink. Think of it in those terms. Then the attacker allows the victim to execute. The cache sets touched by the victim will be determined by the code that the victim executes. In other words, this yellow pattern is determined by the behavior of the victim. The attacker then reruns its code and times the memory accesses it's performing. So what's nice here, from the perspective of the attacker, is that if the victim has evicted the data contents of one cache line, then the attacker will detect the fact because its memory access will be slow. It will incur a cache miss. If the original data contents are still present in the cache line, then the attacker benefits from a cache hit, and the memory access is relatively fast. So the attacker performs this probing process and times all of the memory accesses. That's the basic idea. Once the attacker's harvested all of these timings, we proceed to the second stage of the attack, which is to make use of these timings to extract meaningful information about the victim. And to explain this, I have to give you like a 10-second primer on the El-Gamal cryptosystem. The important thing to understand here is that El-Gamal is a public key cryptosystem, for example, an alternative to RSA, which is the more common choice. And the thing you really have to know is that it involves, in decryption, a modular exponentiation to a private key that is essentially a random bit string. So the goal of the attacker is to learn this private key, to learn the constituent bits of this key. And typically, there are a few hundred bits. I'll give you specifics later in the talk. I've given the mathematical structure of the decryption algorithm here, but actually you don't have to know that for the purposes of this talk. What's important here, the key observation, is that modular exponentiation in the classical square and multiply algorithm, which is the one we'll be attacking, induces different code paths for different bit values in the private key. The way it works is to run through the key bit by bit. And if it encounters a 0 bit, it performs a squaring and a modular reduction. So this code circled in green will get executed. If it encounters a 1 bit, it will additionally perform a multiplication and reduction. So the code path will get extended. It'll then execute the code circled in red as well. So there's a difference in the code path followed when you see a 0 bit and when you see a 1 bit. And this is the fact we're going to exploit to extract the private key. So the important thing here, of course, is that different operations produce different footprints in the cache. So you can see the square operation touches different cache sets than the multiply operation touches different cache sets than the modular reduction operation. And so we're able to take the timings harvested by the attacker in the first stage, the prime probe stage, and classify them to determine what operation has taken place in the victim VM. This is a pretty noisy environment, so classification is not straightforward, and we had to appeal to some basic machine learning methods to do it. We used a support vector machine to perform the classification in particular. So we take these timings, we run them through an SVM, and we get a bunch of what are called labels. These are hypothesized operations in the victim. But we're not quite done yet. Problem here is that because this environment is so noisy, the SVM is going to make some classification errors. So it may mistake a squaring for a modular reduction, and so on and so forth. So we end up with a sequence of labels, but these labels are noisy. And that leads us to the third stage of the attack, namely noise reduction. So we have these noisy labels, but we do have one thing operating in our favor, which is that we have some redundancy in this set of labels. We're actually able to interrupt the victim frequently enough to make multiple observations per operation. So for instance, when a squaring takes place, we'll actually be able to observe it 4 times, so we get 4 labels out of the process. And this redundancy helps us eliminate noise. For this, we have to trot out another method from machine learning, namely a hidden Markov model, which, as many of you know, is a statistical model that presupposes some hidden state in a system. In our case, the hidden state is the sequence of operations performed by the victim, and some labels probabilistically associated with these states. The labels are the outputs of the SVM in our case. So using the hidden Markov model, we're able to deduce most of the operations performed by the victim and eliminate a fair amount of noise from this sequence of labels. That brings us to the final stage of the attack, which is code path assembly. We have another problem here, entirely apart from the noise. When the attacker is sitting on the same cache as the victim, of course, it can observe the sequence of operations the victim has performed and therefore observe the bits of the private key using the techniques I've described. But we're operating in a multi-core environment here, typically in the cloud. So the hypervisor will periodically migrate the attacker away from the victim. When the attacker gets migrated away, of course, it sees nothing of consequence. It certainly doesn't see the private bits, rather the bits of the private key of the victim. So the attacker at that point has to wait until a migration again brings it into contact with the victim. And only then is it going to again be able to read out bits of the private key. So what the attacker is seeing is not the full set of bits composing the private key. Rather, it's seeing snatches of the private key. It's seeing private key fragments. In its view, this is the behavior of the victim. So to reassemble the private key, to determine the full private key, we somehow have to take these fragments and stitch them together. We have to take these little sequences of bits and somehow build up the full private key. Now, this led us down a very interesting path in our research, which I will mention even though it wasn't entirely fruitful. This problem of stitching together fragments is very similar to a problem in computational biology known as the DNA sequence assembly problem. And that problem looks like this. You start with some organism, like a Neanderthal, and this organism has some DNA. You let the organism decompose for a couple of tens of thousands of years, so it looks like this. And of course, this is all we have left of Neanderthals. And the DNA will also decompose. So when you sequence the bases in the DNA, you end up with fragments, very much like the case in our side channel attack. The DNA sequence assembly problem is to take these fragments and stitch them together to reconstitute the original DNA, and therefore figure out what the organism looked like. And in fact, once you have reassembled the DNA, by the way, you can reconstruct the organism. I have it on excellent authority that in the case of the Neanderthal, this is about to take place. But I'm not going to discuss that today. Well, as I mentioned, this is something of a red herring. Unfortunately, our data was too noisy for these techniques from computational biology for DNA sequence assembly to be applied directly. We ended up having to roll our own. But our techniques are vaguely similar to those employed by the biologists. So using these techniques, we're able to take the fragments we recover through these periodic observations of the victim, put them together, and reassemble a complete private key with no errors. There's one small catch here, which is that we had a few erasures, but we were able to fill those in by brute force, because, of course, we have the corresponding public key. So that, in a nutshell, is the attack. Now, we evaluated this attack in an environment described here. The important thing to observe is that we used real code, which is to say code that is in widespread deployment, GNU Privacy Guard with a cryptographic library called libgcrypt. And this environment is meant to mimic the environment found in typical cloud scenarios. For instance, Amazon EC2 uses a setup very much like this, a standard Zen plus a Linux setup.
Are you always running if there's 2 VMs on the system?
In this case, we were, but you could run other VMs, and you may be asking whether the SVM, for instance, is going to misclassify the cache footprint of some extraneous VM as cryptographic material. As I said, I'm skipping over a lot of details. In fact, you can weed out observations of other VMs. They won't look similar enough to the operations conducted by the victim.
Does the attacker always know when the attacked VM is running?
You can deduce that after the fact, again, because any extraneous operations will be classified as unknowns in our hidden Markov model. Again, and I'm sorry I had to skip a lot of details. You can, in fact, accommodate VMs other than the victim in this environment. And in fact, the attacker is running 2 VMs for technical reasons. There are a lot of complexities.
And that's also true of other things the victim may be doing.
And that's true of other things the victim may be doing as well. Yes, you would expect that it's not constantly running modular exponentiations. That's something we're able to account for. Okay. Well, this attack is not easy to mount. It took us, even in a lab environment, 45 hours to extract a private key and a little brute force hypothesis of missing bits once we had reconstructed the key. But this is a demonstration of feasibility. The important point here is that this phenomenon of aggregation of VMs can be dangerous. With a combination of techniques, we were able to demonstrate a viable cross-VM cache-based side channel attack and pull out El-Gamal private keys. And similar techniques would perhaps be applicable to other crypto systems. RSA is trickier than El-Gamal, but not necessarily infeasible. There are a bunch of caveats here. For instance, as I mentioned, I glossed over many challenges in the work, like the challenge of ensuring that we can interrupt the victim very frequently, the challenge of ensuring that during the training phase, when we have to label examples, that we don't end up modifying the footprint in the cache in such a way that we throw off the training. Lots of challenges here. Additionally, you'll notice we didn't actually implement this in a public cloud. We implemented this in a lab environment for reasons both technical and ethical. While extracting cryptographic keys may be hard, I should point out that that is probably the biggest challenge in a side channel attack, in the sense that that's the biggest prize. And it may be possible to deduce other behavior, which is in stronger evidence. For instance, you may be able to tell when an e-commerce server is performing a transaction. So if you want to spy on your competitor to determine the rate at which the competitor is selling some good, that may be feasible, and it may be much more feasible than the attack I described.
So I may be jumping the gun with this question here, but the main thing that I'm wondering at this point is migration, if you were in fact in the public cloud, because you said because there's concerns of being co-located.
Oh, you mean migration from a host or within a host?
From if you leave the host where your victim is on.
Oh, yes, that would be a problem, but in
like measurement of saturation of instances in order to try to get on the victim's machine.
In the experiments we have done in Amazon, we've never observed a migration from a host. We've observed occasionally hosts being shut down, but it appears that migration of VMs across hosts is not common at this point. OK, let's turn to the other aggregation problem. Remember I mentioned this problem of large sets of passwords residing in a single database. Well, RSA has, in fact, recently, at the end of last year, started offering a product to address this problem. And it's a product that emerged from RSA Labs and suggests some interesting follow-on research. So I want to talk about that. The product is called Distributed Credential Protection, or DCP. And as you'll see from the marketing material, it scrambles, it randomizes, it splits, it re-randomizes. It's a little hard to deduce exactly what it does, but I'm assured this is very carefully crafted language. Let me explain to you what it really does. The concept is fairly simple. The key idea is distribution. The idea is that a user's password is stored not in a single database, but across multiple servers. And in the case of DCP, 2 servers to start. So password is, in particular, split in the following way. First, a random pad is generated, and that pad is stored on one server. We typically refer to it as the red server. And then the password itself, with the pad added, you can think of this as an XOR, is stored on the other server, the blue server, as we conventionally call it. So what you'll observe here is that neither server in isolation contains any information about the password. If an attacker breaks into the blue server, it sees the password XORed with a random pad. That's an information theoretically strong encryption. If it breaks into the red server, it's also clear that it's not going to learn anything. All that's there is a random pad. It has to break into both servers in order to recover the password. What's actually stored is the hash of the password. I'm simplifying a little bit, but you get the idea. So what happens when the user comes along and submits a password in the course of authentication, password P prime? Well, the splitting process then is repeated on the client. As a new random pad, R prime is generated, sent to the red server, and then P prime XORed with or added with this R prime, this pad, is sent to the blue server. And at this point, the 2 servers take the difference between the stored value and the submitted value. The thing you'll notice here is that if P prime is equal to P, meaning that the user has submitted the correct password, then you'll get a cancellation here. Right? Then P minus P prime will be 0. And so what you have on the left in this situation is R minus R prime on the left, and that's exactly what we have on the right. So in other words, with this splitting, if the user submits the correct password, the values held by the 2 servers will be equal. So all we have to do to check that a password is correct is test equality. And that's something we can do magically without reassembling the password. In fact, without any interpretable exchange of information between the 2 servers using some crypto magic known as a private equality test. There's a way for the 2 servers to conduct a protocol such that all they learn is whether or not the 2 values are equal. They learn nothing else. And so no information about the password is betrayed to either server. So the 2 servers are checking the password without reconstructing it. The strange thing about this technology is that it's 20 years old. The basic ideas are 20 years old. What DCP is implementing is a form of what's known as distributed cryptography. And I've given you a couple of seminal papers here, one on proactive cryptography to be precise. But distributed cryptography has been around for a long time. And even the specific implementation I'm describing, the one that made its way out of the lab into a product, is pretty old. It's 8 years old. Yet, this is the first broadly available commercial implementation of distributed cryptography. Distributed crypto, for those of you familiar with it, know that it's a powerful and, in fact, fundamental concept in the research literature. So this is really surprising. And a natural question to ask is why it took so long. Well, one important reason is that new technologies generally take some time to achieve a happy convergence of factors, or to benefit from a happy convergence of factors that may be extraneous to or tangential to the technology itself. I had a very nice object lesson, this kind, a couple of years ago when my wife and I went to reback a lithograph, and we found this snippet of paper behind the lithograph. It was a bit of newspaper describing a public demonstration by an inventor of what was essentially an mobile phone, if you will. It was a phone with a battery that communicated without wires, and it worked over, as you can see, a distance of 6 blocks or so. Well, mobile phone networks didn't really emerge in earnest until the 1970s or so. So any guesses as to the year in which this newspaper article was published? Anyone? Any guesses?
1817.
1925. Any real guesses? 1925. The actual year was 1902, which is pretty shocking. Right? So we're doing well with DCP. That's what I'm telling you here. An interesting question is, well, why is the time ripe for distributed crypto? I mean, it's ripe at least in the sense that companies are now willing to invest in products like DCP. And I would argue that one of the reasons is the better distribution that the cloud affords. Remember, I was going to talk about how distribution can help us solve security problems. A major historical objection to distributed crypto was the fact that it's not obvious that breaking into 2 servers is any harder than breaking into 1. And after all, if you've found a vulnerability in one server and you replicate the server, then it's going to be fairly easy for an attacker to break both more or less simultaneously. Right? This is, as I said, a long-standing objection to distributed crypto. But virtualization kind of changes the game. If we have a nice virtualization substrate, then it's fairly easy to run these 2 servers on different operating systems, for example. So one can be running under Windows, the other can be running under Linux. And as you know, many attacks succeed as a result of vulnerabilities in the operating system. So this is a very nice form of diversification. And it's just one of the forms of diversification that the cloud enables. Cloud providers can also easily distribute servers across administrative domains and across geographies, right? There's no reason why the blue server can't run in Washington while the red server is running in Virginia. An additional and attractive possibility is distribution across clouds. We can put the blue server in Amazon, for instance, and the red server in Rackspace. And that's a very powerful form of diversification. It means an attacker has to break into 2 different cloud providers in order to get the underlying passwords. Additionally, there's a very easy migration path for an enterprise to real distribution. Namely, the enterprise can take an existing database of passwords and split it between 2 servers, retaining control of one server, keeping the blue server on-premise, and pushing the red server into the cloud. What's particularly nice about this is that the enterprise can unilaterally decide, for instance, to destroy the database if it wants. And if the enterprise happens to get breached, it knows that the underlying passwords are going to remain secure. One thing I'd like to point out is that distributed cryptography is applicable not just to passwords, but to essentially any sensitive resource. And in fact, you can do general purpose computing in a distributed environment. You can split not just passwords, but private keys and data and many other things. So it's a very powerful concept, and it's one that the cloud offers us nice opportunities to implement in a principled way. There's so many different forms of distribution now at our disposal that techniques from distributed cryptography become quite attractive. Now, DCP is, as I said, based on some old ideas and some old research. But it introduces some interesting new practical research challenges. And I want to talk about at least one of those today. The natural question to ask is, OK, we can distribute passwords. when we're merely testing password equality, can we efficiently distribute other forms of authentication? For example, can we distribute password-based Kerberos? I'm going to talk about Kerberos and why that's not so easy. Or can we distribute the verification of one-time passcodes? These are the passcodes generated on tokens like RSA's Secure ID token, if you're familiar with it. Well, these are generated cryptographically, so they pose much more of a challenge than checking passwords. There's an underlying symmetric key operation in these devices. There are other cryptographic protocols it would be nice to be able to split, symmetric key challenge response, for instance, and other forms of authentication, like biometrics. So let me talk a little bit about password-based Kerberos and what research challenges it poses. I'm going to give you a simplified description of Kerberos. There are many different flavors and variants, and it's a fairly complex protocol. But at its root, it looks like this. The user holds a password, and the server stores a hash of this password. When the user goes to authenticate in what's known as a pre-authentication step, this is just one flavor of Kerberos, what the user submits is a timestamp, the current time, and a ciphertext consisting of an encryption under the hash of the password of this timestamp. So timestamp, encryption under password of timestamp. To verify that this is correct, of course, what the server does is check first that the timestamp is fresh, and then decrypts the timestamp under the password stored for the user. And then, and only then, says OK. Well, here's the catch. In DCP, we were just checking password equality. Here, in order to distribute the operation of verifying the password, we would have to distribute the computation of the decryption function, which is typically something like AES. That's a full-blown cipher involving many arithmetic operations. So that's not easy to distribute. There's quite a bit of literature on this, but for most intents and purposes, it is utterly impractical to distribute AES computations. So it would seem like we're stuck here, right? This would seem to be an impossible problem. We can't extend DCP to enable us to split the verification of Kerberos. And since it's an impossible problem, it's a great research problem. And since it's an impossible problem, of course, the way we solve it is by cheating and changing the problem. So let me describe the cheat. What we'll do is take the original server, and we'll retain the hash of the password on it. And then we'll split. We'll create red and blue servers again. And we will store the hash of the password on both servers. Well, at this point, we haven't accomplished anything. And an attacker compromises either server, we'll get the password. But what we're going to do at this point is mix in what we'll call chaff passwords. We'll mix in a bunch of bogus passwords on both servers. And these sets of passwords will be distinct. So the intersection of the two sets held on the two servers will be the correct password and the correct password alone. Now, when the user goes to authenticate and submits this timestamp and the ciphertext under the correct password of the timestamp, so it's going to go to both servers. And what each server will do is run through the full list of passwords it has and check to see that at least one of them corresponds to the ciphertext. Now, the chaff and the real password will be stored in some random order, and the server will have no awareness of which password is correct. That's the important thing to observe here. So all the servers are going to check is that some one password corresponds correctly to the submitted value. And we accept an authentication is correct if both servers say, yes, this looks to be correct in my view. And another nice thing is here is that the two servers don't have to interact. They can operate in parallel. Well, what does this buy us? As I said, the real password is the intersection of these two chaff-laden sets. So if an attacker breaches only one server, it doesn't get the original password in isolation. It doesn't immediately know the correct password. It sees the password embedded in some candidate set. So the only way for the attacker to breach the system is to start guessing passwords in an attack on the other server. Right? If the attacker breaches the red server, for instance, it can submit any of the passwords resident on the red server, assuming it cracks the hashes, and the red server will say yes. But in order to attack the blue server, it has to guess which of these values is the correct one. And that's something it can do only online. And that's a detectable event. Because when the attacker is doing this, one server will be saying, yes, this is a correct value. The other server will be saying, no, this is an incorrect value. That's a situation that will almost never arise under benign conditions. Now, there's a catch here. I said we were cheating. The problem with this protocol is that if an attacker observes a real authentication, it will, of course, observe the correct value. So this is really only good against bulk compromise of passwords in a passive model. Attacker breaks into a server, pulls out the database, starts cracking hashes. And so it's not as strong as true splitting. It doesn't give us the same security guarantees that DCP in its pure form does. But it's a lot better than current approaches. And the nice thing is that it's legacy compatible. We can use this with existing Kerberos systems. And it doesn't require any interaction between the two servers, as I mentioned, which is a bonus as well. Another important question arises here, of course, is how we fabricate the chaff, right? How do we generate passwords that look real?
Why can't the attacker try to use all the passwords and see which one succeeds?
So the attacker can do that, and the attacker will do that, but every try is an online event. Right? In order to determine whether a password is correct, the attacker, having breached red, has to submit the password to blue. And so, as I mentioned, what's going to happen is that the relying party, the one that's interpreting the yeses and nos of these two servers, will see the red server say yes and the no server say blue, and that's evidence of an attack. So the attacker is going to betray the fact that the breach has occurred, right? With high probability. There's some probability the attacker will guess right the first time. So that's the important point. What it does is convert an offline attack to an online attack, and one that's detectable. So as I said, one challenge here is in generating these chaff values. Right? If we don't generate these chaff values intelligently, then an attacker is going to be able to distinguish the real one from the chaff values. So you might think, for instance, that you would just generate some random strings. But if the correct password happens to be, say, the word Seattle, and all the other passwords are just random-looking strings, an attacker is going to know which is real and which isn't. Thankfully, there's a fairly simple way of generating chaff, and one that involves very little storage overhead. Namely, what we can do is use other users' passwords as chaff. So we construct this kind of bipartite graph with users on the left and the full set of passwords on the right. And we just map each user to some random subset of hashes. That's how we construct the chaff set. So Alice's real password may be P3, or I guess in this case P1, but she's going to have Carol and Darlene's passwords acting as chaff on her behalf. And of course, we can do this for all users. And depending on the degree of the graph, we get more or less strength in this mechanism. Another nice feature of this approach is that it's pretty easy to extend to other credentials. Right? More or less the same approach, for instance, can work for biometrics. Alice's real fingerprint will be sitting on the system, but it will be protected through obfuscation, embedding with the fingerprints of other users. Right? Same idea, and similarly feasible to implement in practice. Okay, well, that more or less concludes my talk.
Sorry, quick question on the last one.
Yeah.
You have to have the two bipartite graphs be distinct?
Yes, they do have to be distinct. So the important point is that the intersection between the two sets held by the servers be the correct value exactly.
So how do you guarantee that? By communication? Or?
Well, you can assume you can generate all of this during a setup phase. You can do a lot of this offline, so it's not too hard to guarantee that. Okay. To conclude here, aggregation is a trend accelerated by clouds in the two ways that I mentioned, and it carries certain dangers. I talked about two of those dangers, one being aggregation of passwords, and one particularly virulent one, namely side channel attacks, which is possible even to exfiltrate a cryptographic key. Distribution is another process facilitated by clouds, but it's one that can improve security. For example, we can do distributed cryptography in the way that we do with DCP. And I should mention, incidentally, that although DCP relies on only 2 servers, we can, in fact, distribute to an arbitrary number of servers. And we can build threshold schemes. We can, for instance, construct a scheme in which, as long as 3 servers are operational out of a total of 5, we're able to perform an authentication.
So with DCP, does the failure point then become the thing that actually accepts the user password before it splits it up into the 2 servers? So
yes, it does. So that's actually a very good point, that DCP protects against bulk password compromise. It doesn't protect against users succumbing to phishing attacks, for instance. Right? And it doesn't protect against compromise of endpoint devices. One reason that we focused on the problem of bulk password compromise in the product is that enterprises are not really responsible for mishandling of passwords by users, or at least they disclaim responsibility for user abuse of password systems. What they are liable for is massive breaches of their own system. So for instance, LinkedIn, as you know, recently lost 6.5 million passwords. That's a really serious event. That's the type of thing that DCP is meant to protect against. LinkedIn's users are presumably being phished on a constant basis, but that's not something that LinkedIn takes responsibility for.
DCP does, so if I remember correctly from a couple slides back, you have something that the user submits a password to, and then it does splitting up and sends to the revenue server and maybe the comparison. But that's something that accepts the user's password is still living on the server side, not on the client side. Or do you push a client out to the user?
That's a good question. There are a couple of ways of deploying it. So one is to put an agent on the client, and that's the preferred way of deploying DCP. The other deployment mechanism or method you suggested of having a splitting server is a good stepping stone to this better practice. What you'll observe is that passwords are only exposed ephemerally on that intermediate server. So you still get stronger security, but it's not ideal.
So by using other users' passwords as chaff, if the attacker doesn't care whose account they compromise, can't they just switch it around and try the password with Alice, then try the password with Bob, which is something that presumably would be less likely to be detected since people do type in the wrong password on a fairly regular basis?
Well, what will happen, so it depends on how the attacker mounts the attack. If the attacker has to get the right password for the right user. And if the attacker, as I showed, uses a password that's correct for a given user on one server, lies within the chaff set, but gets it wrong with respect to the other server, that's a detectable event, and that's a telltale sign that an intrusion has taken place. Well, I'm telling you about the dangers of aggregation and the benefits of distribution, but actually I could have given the opposite talk. Right? I could have talked instead about the dangers of distribution. For example, if you're distributing across services, you can be composing services dangerously. Right? You can be composing services in such a way you end up degrading security. And I could talk about the benefits of aggregation. After all, by aggregating resources in a single cloud, you create economies of scale in services. You centralize resources in such a way that you can rapidly deploy patches. You make administration easier. So I could have given you exactly the opposite message. So the message I want to leave you with is that it's not that aggregation is inherently bad and distribution is inherently good, but rather that cloud computing is causing a redrawing of resource boundaries in a fundamental way, one that impacts security deeply. And we need to understand this impact, and we also need to understand how to control this redrawing of boundaries, how to influence this redrawing of boundaries to ensure better security rather than weaker security. Okay, that concludes my talk. Thank you.
This is a great talk. Thank you. So I've always been fascinated by the side channel attacks paper. So in the architecture community, we see almost every year, 2 or 3 people finding new side channel attacks that could potentially be implemented. So my question is, do you think there's a principled way of preventing them, or are we always going to be playing catch up, like, oh, somebody clever finds one, you have to go and find an ad hoc solution for that. And so do you think it's a principled way of avoiding side channel
I think it's a
attacks?
great research problem for a faculty member working on computer architecture. Oh, I seriously do, actually.
Right, well, the architecture is not the only source of side channels, right?
No, that's fair.
So,
It's very hard to defeat side channel attacks, well, to come up with a comprehensive and principled defense against side channel attacks. The lesson as we see it is that if you've got sensitive information on VMs, you shouldn't put them on the same physical host, because no matter what, they're going to be sharing resources, and side channels of some type or other will exist.
right, but the network could be a source of side channels. Right?
Yeah, they abound in any computing system. It's really hard to reason in a, as I said, a comprehensive way about them, and even a principled way about them. Yeah, so they're real danger. Thankfully, the attack I described is pretty hard to pull off in practice.
Yes, I kind of have an answer for Louise's question and also a question. There's a large body of work on exposure. What? There's a large body of work on exposure resilient cryptography, which seems to do exactly this. Try to give a principled answer to this problem. So it seems to me that, for example, at least in theory, should solve the first type of attack that you're talking about.
Yeah, well, that's a very good point, and a point I probably should have emphasized in the talk. The reason we chose to attack the square and multiply algorithm is that it's actually a use of that algorithm is deprecated practice. It's known to be vulnerable to side channel attacks, and it should not be used today. For some reason, it's present in libgcrypt. There are better, as suggested here, side channel resistant cryptographic algorithms. But an algorithm is only side channel resistant within a given model. And the task of an attacker, of course, is to work outside the model. So you may have a cryptographic algorithm that's resistant to side channel attacks involving the cache. Well, there are other potentially dangerous side channels, like power consumption, right? That's one that you've worked on here, and probably numerous others. So you can certainly be principled with respect to a given model, but to be comprehensive at the same time is pretty challenging.
But I think both of those models are captured by the approaches that we know. The approaches that just refresh the key. As far as I know, I'm not an expert on this, but.
Yeah, I mean, I'm not an expert on side channel resistant cryptographic algorithm design, so I don't know exactly how broad their models are. There are certainly algorithms that are designed to be resistant to specific attacks like timing attacks and cache attacks of the type described here, but I don't know how broad they truly are.
Any more questions?
So you mentioned that RSA is safer from side channel attacks. Is it safer just because it's more complicated, or?
Yes. Well, in particular, the RSA algorithm is typically implemented with an optimization known as Chinese remaindering, and that extra algebraic step would thwart an attack of this kind. So we actually started out trying to attack RSA, and then reverted to an attack on this simpler crypto system.
Do we know if any big companies are using this distributed scheme on the cloud already, and does it really provide as much protection as we'd like it to?
Well, as far as we know, as I mentioned, this is the first broadly available commercial implementation of distributed crypto in the sense of active computation. There are companies that will split data, which is a kind of rudimentary form of distributed crypto. And you ask a good question. I don't know that anyone has studied the question of longevity of the fragments once you've distributed them, or long-term resilience to compromise if they're distributed across multiple providers. I think these are open questions.
So you've talked here about opportunities for security in the context of cloud. When you think ahead to other opportunities for security research, are there other topics that you're very excited about in addition to cloud security?
Well, I'm convinced that everything will be cloud security soon, in the sense that endpoints are going to become simpler, as in the Chromebook model, and therefore this phenomenon of aggregation will accelerate. So, I mean, of course, there are always going to be niche security problems. There will always be things like sensors and RFID tags that require some thinking about security in constrained environments at the endpoint. But I really think this is going to be a central topic, if not the central topic. And of course, it's multifaceted. One can think about crypto in the cloud. One can think about how to manage security logs in the cloud, which is a really interesting problem, actually, because ideally, tenants or auditors would like to have access to a cloud provider's security logs. But revealing the security logs of the cloud provider to one tenant could betray information about the behavior of another tenant. So how on earth do you go about sanitizing these things if you're going to start passing them around? So I think it's essentially an all-embracing security topic, or I think it will be, more or less.
So you're saying when you generate chat passwords, you can't just use random strings because an attacker can distinguish between like a regular passphrase and a random string, but just wondering how that's the case if they're all hashed, all the passwords are hashed.
Well, typically an attacker will, after capturing password hashes, go and crack the passwords. And with enough computing power, given the hash functions typically in use today, that's feasible for a large subset of passwords deployed today. Now, you're right. You could generate a chaff password that would completely resist cracking of this kind. But that would probably be a sign to the attacker that this is a piece of chaff, and the thing that I can crack is the real password. And so you have to be very careful about how you construct the chaff. And that's what's nice about using other users' passwords as chaff. You're drawing from the same population of users as the original user comes from, and you know that you're presenting the adversary with a fairly consistent lexicon.
Great. Well, let's thank Ari again.
Thank you.